Quantum teleportation between independent photons is no longer theory. It just became reality in a way that changes everything we thought about the future quantum internet. Today on Thinking to Q, the spotlight is on a radical new experiment where scientists created an unprecedented quantum link between particles of light that do not even come from the same source. This is not a small step in physics. This is a direct blow to the idea that the quantum internet is a distant dream. In late November 2025, a team from the University of Stuttgart made history. They successfully sent quantum info between photons from two different quantum dots, which are like separate light sources. That means the entangled photons that form the backbone of a quantum network do not need to come from the same crystal, the same chip, or the same device anymore. For the architecture of future quantum networks, this is a brutal and elegant game changer. Until now, many demonstrations of quantum teleportation depended on carefully tuned, identical sources. The message was always the same. Yes, it works, but only under ideal and fragile laboratory conditions. This new experiment destroys that comfort zone. Two independent quantum dot emitters were used to create photons, whose quantum states could actually be teleported from one to the other, even though they are born from different physical systems. This makes the blueprint of a modular, scalable quantum internet much more realistic. The setup used a fiber of about 10 meters, something close to 33 feet, to guide the light and perform quantum teleportation between these distant photons. At first glance, this distance may sound modest compared to satellite experiments, or hundreds of kilometers of fiber. But the real shock here is not the distance. It is the fact that separate quantum sources are now talking to each other at the level of single photons and quantum states. This is the missing link that allows many small quantum devices to behave as one powerful network. Teleportation fidelity above 70% was achieved. In classical terms, that may sound low, almost like a bad connection. In quantum networking, that number screams something else. It says the platform is already in a regime where error correction, better engineering, and improved interfaces can push this straight into the territory of practical applications. Quantum links created this way can be purified and stabilized by protocols designed to handle exactly this level of imperfection. This new quantum link is not just a physics curiosity. It is a proof of concept for real-world quantum repeaters. To build a global quantum internet, you need devices that grab fragile quantum states, store them, and then forward them without reading or copying the information. Classical repeaters amplify signals, but quantum physics forbids copying unknown states, which makes repeaters much more subtle. What Stuttgart has shown is that independent quantum sources can be wired into such a chain, turning teleportation into a practical networking tool instead of a laboratory stunt. The breakthrough also exposes an uncomfortable truth for cybersecurity and geopolitics. Countries and companies that dominate this type of technology will control the next generation of secure communication. Quantum links based on teleportation and entanglement promise encryption. That is not just hard to break but physically impossible to hack without leaving clear traces. The experiment with independent photons is proof that this infrastructure can be distributed across different devices and locations, not locked away in a single monolithic system. This is bad news for anyone betting on classical cryptography as a permanent fortress. Traditional encryption relies on mathematical problems that powerful quantum computers may eventually crush. A quantum internet built from teleportation-based links does not play that game at all. Its security comes from the structure of reality itself. Any attempt to intercept or copy the entangled photons ruins the quantum correlations and exposes the attack instantly. The Stuttgart result is a loud signal that this new paradigm is getting closer. From a technological perspective, the use of quantum dots as photon sources is also highly strategic. Quantum dots are compatible with semiconductor fabrication and integrated photonics, the same industrial ecosystem that manufactures chips and optical components today. Linking independent quantum dots via teleportation proves that we can dream of quantum network nodes built on scalable platforms, not exotic one-off lab devices. This is the route to quantum routers, quantum modems, and full quantum network cards. Publishing this work in a major journal like Nature Communications is not just an academic badge. It positions this result as a reference in the roadmap towards functional quantum communication networks. This experiment feeds directly into other advances that extend the range of quantum links, improve stability in noisy environments, and combine cheap commercial fiber with high-end quantum devices. Step by step, the walls separating our classical internet from the quantum layer are collapsing. On Thinking to Q, this kind of news is not treated as distant speculation. It is a clear sign that the infrastructure of the future internet is taking shape now. Quantum teleportation between independent photons is an explicit declaration that quantum networks will be modular, distributed, and brutally more secure than anything we use today. The quantum internet is no longer a promise, it is under construction. And this new quantum link is one of the clearest building blocks laid so far.